Hello, my name is Rania Kabani, and today I'll be discussing palladium cross-coupling reactions by the Suzuki-Miyamura reaction mechanisms and their advancements. The Suzuki-Miyamura cross-coupling reactions earned the Nobel Prize in Chemistry in 2010. It demonstrates transition metal catalyzed cross-coupling reactions, and they are among the most synthesized reactions to this day. They have many applications in all branches of chemistry, such as the agrochemical industry, the pharmaceutical industry, and in materials science as well. The reaction begins with oxidative addition. This is the first step in the catalytic cycle, and the bond between the heteroatom and the organic R group is broken, and two new bonds are formed with the ligand and the palladium 0 metal complex, which oxidizes the metal. The formation of these bonds increases the oxidative state of the metal by 2 units, and the ease of oxidative addition is influenced by the strength of the carbon bond, and therefore this step is dependent on the ligand in the active species because many different ligands have been tried for this Suzuki cross-coupling reactions. It's actually known for, trying out, several different hundred ligands. The next step is called transmetallation, and in this reaction step, the organic group is transferred from one metal to another, and this can be compared to an exchange of ligands between two metals. In the case of the Suzuki reaction, the transmetallation step is an exchange between the organic group of the boron species and the metal complex. In this case, there's a palladium complex with a halogen or a pseudo-halogen ligand. Also, this is the most characteristic step of the cross-coupling reactions, but differs in the nucleophile being used. Reductive elimination is one of the last steps in completing the catalytic cycle. In this step, 2 bonds are cleaved, and one bond between the 2 organic groups in the cis position is formed by reducing the palladium 2+ to palladium 0, and the active catalyst is regenerated. The oxidative state of the metal is reduced by 2 units, and the reductive elimination step is affected by different factors such as the ligands, as mentioned. The mechanism of the Suzuki coupling reactions is similar to the Heck reaction. The difference is in the transmetallation step, where the organometallic reagent, either zinc or boron, is transferred. In cross-coupling reactions with the carbon, with an sp3 carbon, there are several issues that can impede the reaction, and due to these issues, there was a need to find different ligands, metals, and conditions to promote the cross-coupling reaction. The ligand is crucial in these reactions because its steric and electronic properties can have a major impact on the reactivity and accelerate the mechanism of the cross-coupling reaction. So in an effort to overcome the limiting factors of palladium reactions, the use of palladium DPPF chloride as a ligand gave optimal results when used as a catalyst, and the DPPF monoalkylated the dichlorobenzene, and there were advancements made to generate these 2 pyrazidone libraries as shown here. In the past decade, palladium catalysts have also been used in PD-Pepsi, which stands for pyridine enhanced pre-catalyst preparation, stabilization, and initiation. And this is a highly reactive pre-catalyst for the Suzuki cross-coupling of amides. One caveat, however, is when using amides as an electrophilic partner, there's high resonance stabilization, which results in low reactivity towards the carbon-nitrogen activation by the metal. However, the PD-Pepsi proved to be very effective in activating the carbon-nitrogen bond, and the benefits of this reaction are that it's simple and inexpensive to prepare Pepsi, and lastly, and most importantly, that the amide carbon-nitrogen bond activation is the most useful when undergoing cross-coupling of amides. Also, with the palladium Pepsi reactions, they found that the catalyst promoted the coupling of multiple amides, and it yielded very high yields. The reactions were also conducted at 40 degrees Celsius, contrary to the routine of using 80 degrees or 110 degrees. And the higher temperatures showed a minimal improvement in catalytic efficiency. So this gave rise to the idea that, these cross-coupling reactions don't need high temperatures, and therefore it is more environmentally safe and conscious to use catalysts that have a potential to work on a variety of amides, whether they are electron-rich, electron-withdrawing, heterocyclic, or even sterically hindered. All of them were responding well to this catalyst. So while this has been one of the most synthesized reactions of all time, there's still a lot of work to be done. And cross-coupling reactions, they're not doing the same reaction each time. They're using different ligands, they're using different metals. But what they found was, palladium is a much better catalyst for the cross-coupling reactions. And to this day, palladium catalyzed cross-coupling reactions are among the most commonly researched and synthesized reactions, and they are extremely useful and accessible. The yields are excellent, and the method of conducting the reaction is quite inexpensive. The main focus of recent studies with respect to the carbon-carbon coupling reactions has been to develop catalyst systems characterized by high yields and selectivity, as well as easy handling and prolonged use. And despite the extensive studies of these reactions, the synthetic community still believes there's work to be done, such as with oxidative couplings and oxidative Heck reactions using air. Other synthetic chemists are striving to conduct Suzuki reactions in a solvent-free or solid-state method, which solid-state methods are really big in material science. This could be more environmentally friendly due to the mild temperatures, as mentioned earlier, the low waste production, low toxicity, and therefore provide avenues for green chemistry. They also are looking for structures that have high tolerance for functional groups, such as the organozinc compounds, and this could assist in the reduction in the steps of synthesis, so less steps, making it even more simple. And there has also been a need to conduct Suzuki type reactions in water rather than any other solvent because, again, it is more environmentally friendly. However, the limitation with this is that a lot of the substrates have poor solubility in water. So this is definitely going to be one of the more difficult tasks of the synthesis. So thank you for listening and have a great day.